So we would like to dive in a little bit more to the DRAM performance metrics. Before we do that, we need to highlight that the DRAM addresses are divided into row and column. We have a RAS, and you can have like referred to as a CAS. RAS is row access drop. CAS is column access drop. This will trigger the row. This will trigger the column. Meaning one will specify where is exactly the row, and one will specify exactly what would be the column, the RAS and CAS. But we need also to highlight some definitions. One of these is basically latency. Latency is just time to access one word. There is also another expression, it's called access time. The access time is just as usual, defined whatever like you would like to need until you get whatever you have asked for. This is just the access time, my normal definition. Here is also the same, time between whatever you request and when the word that you have requested is either read or written. And the read access and the write access, the read access and the write access times can be different. Also, there is cycle time, it's just a cycle. So the time between successive read or the time between successive write, as an example. Usually the cycle times is greater than the access time. So this is basically is greater than this thing. There's also another thing called the bandwidth. What is the definition of the bandwidth? It's how much data can be supplied per unit time. How much is the data that we can supply? So suppose right now that we have a pipe. And inside this pipe, there is a flow of a certain liquid. And we would like, for instance, to calculate the flow rate or to get a relation of the flow rate. So how much is the flow that can be able to flow? How much of that liquid can flow in that, or the rate of the flow in that particular pipe? Of course, by logic, the bigger the size of the pipe or the cross-sectional area, the higher I'm expecting would be the flow rate, or the higher that actually this particular channel can accommodate. Correct? The same happened with whatever like the velocity of the liquid inside the pipe. This also will affect the flow rate. So if I want to multiply the cross-sectional area of the pipe, multiply it by the velocity of the whatever the flow of the liquid, it will give me the total flow rate in this particular situation, or the total flow. Here is the same. Instead of the pipe, we have a channel. And instead of the cross-section area, we have the width. So multiply the width of the data, multiply it by the rate or the velocity, yes, at which it can be used, then it will give me the bandwidth. The other example, it will give me the total flow, but it is, by analogy, the same concept. The bigger, of course, the width, I'm expecting would be the bigger or the higher bandwidth. The bigger with the rate or the higher the rate, also this will affect positively the bandwidth and so on and so forth. So here is the shape of a classical DRAM operation. With a classical DRAM operation, you have multiple rows, let's say like n rows, you have n columns, but you have m bits. As we mentioned here, you will specify, so this is as an example, one row. This is one row. And this is one of the columns. Of course, you have multiple columns. But when you specify a row and specify a column, then you specify a certain particular location. Each of these locations basically have the depth of m bits. So this is basically here m bits. But you need to specify a certain row and a certain column in order to go to that particular location. If I would like to go to another location, I have to specify also the row and the column. If I would like to go another location, I have to specify the row and the column, and so on and so forth. So every time I specify the row, I specify the column, and then I can read the particular m bits. and so on. So specify the row, specify the column, and then read or write. Specify the row, specify the column, and then read or write, and so on and so forth. This here is basically the access time, as the definition exactly that you mentioned, the time between the request and when the word is read or write, so the time between the request and when it is read or write. And also we have the cycle time, which is the time between basically a successive read or a successive write. Try to see that with a different analogy when we have a little bit of fast or page mode DRAM operation, meaning that we have one row address and then we are accessing different columns and so on. So we're accessing this and then this and then this and so on and so forth, but they are all in the same row. Meaning that I don't, in this situation, I do not have to specify each time the row and the column. I just need to specify first the row and then the subsequent column, 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 and so on and so forth. And because of that, this will be much fast access in this particular situation because I didn't change each time the row. I'm just changing the column, but it is in the same particular row. And in this situation, I have to specify the row and then column, 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 and so on and so forth. And each with this column, I will read the M bits and M bits and so on and so forth. Here, as you can see, this will be my cycle time. Another situation, if I have a synchronous DRAM. Synchronous means that now I need a clock. And I will read only with the clock. So I will specify row and column and then begin read and write with the clock, either with the positive edge or the negative edge or both of them and whatever the things is, and then begin to read the certain M bits with the clock. So given this information, let's try to move forward with this particular information. So now we have a CPU. We have a cache. We have a bus. And we have the DRAM. I have 32-bit data and 32-bit address bus per cycle. So let's have some assumption that I have one memory bus clock cycle to send the address. I have 15 memory bus clock cycle to get the first word in the block from the DRAM. I have 5 memory bus clock cycles for the second, third, and fourth word, meaning different columns. What does that mean? Meaning that in order to specify the very first word, I have to specify the row and the column. Correct? Or each time I would like to specify a word, I have to specify a row and a column. And this will cost me 15 bus clock cycles. But if I have already specified the row and I just need to specify the column, this only cost me 5 memory bus clock cycles. Then I have 1 memory bus clock cycle to return a word of data. Also, how to get the bandwidth, the number of bytes accessed to the cache per CPU, basically in this particular per memory block bus clock cycle. We'll see an example right now, and hopefully you will understand that. Suppose again that we have 1 word wide bus, 1 word blocks, and we have a block size that is only 1 word. Suppose that you have a cache miss. That means that my pipeline will have to stall for the number of cycles, of course, required to return 1 data word from the memory. Let's see how we can calculate that. First, I will have 1 memory bus clock cycles to send the address. Then since it is only 1 word, and in this 1 word I have to specify the row and the column, I have to pay 15 bus clock cycles to read the DRAM. And at the end, I have to pay 1 memory bus clock cycle to return the data. If you add 1 plus 15 plus 1, it will give you 17. So how to calculate the bandwidth? Now, in order to miss one word, I have to pay 17 cycles, clock cycle, correct? One word. One word means how many bytes? 4 bytes, correct? So that's 4 divided by the total clock cycles. So this means that I have 0.235 bytes per memory bus clock cycle. So this is my bandwidth. Of course, the higher the better. How I will get higher? I will get higher by increasing these, or by decreasing these, or by both. Correct? Yes, if 17 is less, that is less number, then that total number will be more. If 4 is larger, then of course it will be more and more. Let's take another example. We have one word wide bus, but instead of one word block, we have 4 words block. But the question that you need to ask with these 4 word blocks, are these 4 word blocks in different rows, or are they in the same row? Because these 2 calculations will be different. They said, no, assume that each word is in different row. So each of the words is in different row. So how much I'm paying? Again, the very first thing is the same 1 cycle to send the address. Then 4 multiplied by 15, because each word will cost me 15 in this case, because each word is in different row. So I have to specify the row and the column. Again, in another place, the row and the column. Another place, the row and the column. 4 different times. Each time, it is costing me 15. 5, 5, and 5. 15. So 4 multiplied by 15 is basically 60. Then also, as usual, it's 1 cycles to return the last data. If you do all of these calculations, it is 62. Oh, I mentioned, I guess, something wrong here. This actually, in order to get like a higher number, of course, this will be less correct. So here, how to calculate the bandwidth? Bandwidth, again, it is 4 words. So 4 multiplied by 4, but 4 multiplied by 4 use 62 clock cycles. So 16 divided by that is 0.258 as opposed to 0.235 here. So of course the bandwidth is less here. Let's take another example. They are still 4 words block, but all of these are in the same row. So again, 1 cycle is to send the first address. And then I need to specify the location of the 4 words. The very first word, I have to specify the row and the column. So I'm paying 15 cycles. But any word, any subsequent words, I just need to pay 5. I need to pay 5 clock cycles, because I have specified the row and the column with the first one. Any subsequent columns in the same row, I just need to pay 5. And that's why I have here the very beginning 15, and then plus the rest, the 3 words multiplied by 5 will give me 30. Same 1 cycles to return the last data words. So the total will be 32. What is my bandwidth? Is 4 multiplied by 4. Why 4 multiplied by 4? Because I have 4 words and each word has 4 bytes. So 4 multiplied by 4 divided by 32, it's giving me 0.5. As you can see, as opposed to 0.2, of course, this 0.5 is much higher bandwidth. And this is, of course, expected since all the words are in the same row. Let's take that example. Assume I have an instruction cache miss rate with 2%. I have a data cache miss rate with 4%. The miss penalty is 100 cycles. My base cycles per instructions is 2 without any stall. Do you remember the same example that I mentioned, like with the slides? I'm introducing one slide per minute without any interruption, without any question, without any answering. It's just the base or the basic. The frequency of all load and stores is basically 36% of my instruction. So 36% I have to access the memory. So how to calculate the miss cycles per instruction? With the instruction cache, I'm telling you that 2% is my miss rate. And with each miss, I have to pay 100 cycles. So 2% out of the time you are missing. But each miss is 100 cycles. Each time you miss something that is in your desk, you have to pay 15 minutes going to the main library to bring that thing. Or you have to spend 15 minutes to that particular location to bring whatever you are missing. 2% out of the time you are missing. So you just multiply 2%, multiply it by whatever you pay for each time you miss. Here, the same things, to 2% multiplied by 100. The D-cache, the miss rate is 4%. So I am missing 4%. Okay, so the D-cache is 4%. So I multiply 4% with the same concept, multiply it by 100 clock cycles. But there is another parameter that I need to add with the data in this particular situation, that I'm not always accessing the memory with all of my code. Correct? It is only 36% of my code that has load word or store word. So 36% out of the time, only I am accessing the memory. That's why I have to multiply by 36%. So 36% multiplied by 4%, multiplied by 100 cycles, gives you 1.44. Of course, I don't have to do this with the instruction cache. Since the instruction cache, I usually access just instruction after the instruction, independent of it is load word or store word. I always have to access the instruction memory in order to bring the next instruction. So then the actual CPI will be my base plus my overhead. So where is my overheads? This is overhead, and this is another overhead. So 2 plus this plus that, it will give me 5.44. So this is my actual CPI. The ideal CPI is 2. If you divide this by that, it will give you 2.72, which gives you an indication that this guy is 2.72 faster than the actual CPI. Also, the average access time, as we mentioned earlier, this is defined as the hit time plus the miss rate multiplied by the miss penalty. This is AMAT. Do you remember when we mentioned earlier that the miss rate and with the miss penalty, and we mentioned that we need something to combine both, and we said, okay, we'll multiply this by that plus the hit time, and then we'll have another graph. This is basically the AMAT. Let's take that example. CPU is 1 nanosecond clock. My hit time is 1 cycle. Miss penalty is 20. Miss I-cache miss rate is 5%. What is my AMAT? Just direct substitution. The hit time is 1. So this is 1. Plus miss rate is 5%. So it is 5%. Multiplied by miss penalty, my miss penalty is 20. So if you do this, you will end up with 2 nanoseconds. 2 nanoseconds is 2 clock cycles. So just as a performance summary, when CPU, of course, performance is increased, the miss penalty becomes more significant, decreasing the base CPI. So of course, greater proportion of time will spend on the memory stalls. So if the difference between the basic CPI and the actual CPI is large, so of course, a lot of time I spend on memory stalls. Also, if I will increase the clock rate, any stalls will account for more CPU cycles, because if it is the same time, but with higher rate, so it's basically account for higher clock cycles or more larger amount of clock cycles. And that's why, of course, with the cache, I can't neglect whatever is happening with the cache if I would like to evaluate the performance of my system. It's extremely important in this situation. So we would like to think actually with other ways to reduce the cash miss rate. And the question that has been raised is there is ways that we can use in order to reduce the cash miss rate? The answer is yes, but we need to think with each other on the situation while it is evolving. So let's think about it from the very beginning, not as we are giving you the solution. So the idea, if you recall earlier, we had the cache, we had the main memory, and we have what we call direct map, meaning that there is a location here, and there is multiple locations in the main memory that all are sharing the same locations. Back to the example of the compound and the parking lot, we have mentioned that since we have, unfortunately, large number of students, we cannot accommodate also a large number of parking spots inside the compound. But luckily, we have been able to accommodate for each apartment a parking spot. And we mentioned accordingly that any students that lives in that particular apartment could use or share that particular spot. So at the very end, many to one, many students have been mapped to parking spot, one parking spot, many to one. So if this is the case, this is my parking spot, I might say that this parking spot belongs to apartment number 1. This parking spot belongs to apartment number 2. This is to 3, and so on until apartment number n. And since this apartment, as an example, has 5 students, so all of these 5 students can share this only one spot. Only one spot. And we found that unfortunately, this kind of mapping has not that good of a performance or of a missing rate performance. Has a little bit of higher missing rate. And the idea that we need to think about is how we can relaxing that. Forget about the cache, forget about the main memory. Think about right now that we have a compound and we have number of students and we have parking spots. I'm giving you this problem to solve, given that you will not change the total number of students living in the compound, and you will not change the total number of parking slots available. How you can change the way of mapping in order to relax a little bit any congestion or any problems of the mapping of many to one. A clever manager came and said, I have an idea which will not affect the total number of students, and also it will not affect the total number of parking spots available. Let's do it that way. Instead of mapping each of the apartments to a location, we will make groups. We will say that we will make, for instance, a group of 2. So this group of 2 is one group that belongs to also apartment 2 and apartment 1. I still didn't change. However, what I am saying right now, that any students in either of these apartments can park either here or here. Does that relax a little bit? Yes, it may relax a little bit. Because, for instance, if we have seasoning situation, there are seasons as an example, or maybe the students are going back and forth or are not always there. So now I'm giving a little bit of more flexibility, because as a manager, parking lot manager, I don't want to see a situation where there is 5 students would like to park in a certain particular location and can't find a parking slot while there are other spots available in my parking lot. No one is using them. So let's do the grouping. Because there may be a situation that there is one apartment has a less number of students, for instance, that is living at that particular day. Or maybe not all of these students have cars in that particular, or whatever the reason is. Or maybe these apartments, usually students return in the same exact time, but the other apartments, they are returning in different times. Or maybe this apartment, they return very late. This apartment, they are returning very early, or whatever the situation is. I'm just trying to relax it a little bit. And with this same idea, instead of having a group of 2 in one set, I may say I can have all of these as a group in one set. Accordingly, from apartment 1 till apartment M, or let's say 10, all of these can park in any of the spots. Any students, meaning associated with this apartment, could park in any of these particular group or set. Does this relax a little bit? Yes, it might relax. I didn't change the number of students, total number of students. I didn't change the total number of slots. I didn't change my memory size. I didn't change my cache memory size. Both are the same. I just changed the way of allocation, where to park. So the benefit right now that we have a little bit of more flexibility, but what is the drawback? The drawback right now, that each time I would like to park, I have to search for a parking spot in my slot number. Correct? Or my set number, sorry, my set number. So if my set is all of these, so I have to search for a slot available in all of these. So it will take more time, as opposed to the direct map, because the direct map, I know exactly the location where I should park. So I will go directly to that location. I will search. If I found available, I will park. If I didn't find it, that I won't park. I will not spend that much time to access that particular spot. Otherwise, or as opposed to the set or the groups idea, that I have to go all the way to all of the parking spots that are grouped together in one set to see if there is something available or not. But you might say, okay, that's fine, but it's not like costing me a lot. Yes, I agree. But that depends on how many I'm grouping together. If I'm grouping a small amount of numbers, then of course, yes, I agree. But if I am grouping a huge amount of numbers, then you have to spend a huge amount of time in order to find the spot. In terms of memory, in order to know exactly where to park, if you have like all of these different spots available for you, you need to search. Or you can use a comparator that can give you the answer directly. But unfortunately, a comparator will cost again area. And that's we need to avoid in some particular cases. So now we have understood that there is a way of a little bit of more flexibility, and with grouping or having sets available might be a good idea. And this is what we refer to as n-way set associative cache. We have n ways to do that. We can group 2 of them, we can group 4 of them, we can group 8 of them into one set, and so on and so forth. Another one came and say like, okay, no, we have actually another idea, which will give even more higher flexibility. We will not give any restrictions to any of the students that are available in that particular compound in terms of where to park. Meaning that anyone in the compound, as soon as you are associated with the compound, You can park in any place. You can park here, you can park here, you can park here, you can park there, all the way till here. Any place. You can park any place. There is no restriction. Great flexibility. Of course, the probability of finding a spot available would be a little bit higher, correct? But again, what is the drawback? The drawback right now, that suppose that all of the parking lot is full and only this is available, but unfortunately you begin the search from here. So you went all of the way, all of the way, all of the way until you went to that particular spot. So you spend a huge amount of time until you found what you are looking for. Or in terms of the implementation of the hardware, you have a huge, big comparator in order to compare all of this spot and just give you the answer. This is, of course, implementation-wise is different. But flexibility-wise, it's fantastic. It's very high. We have a very high flexibility where to park. But the problem that if you have, for instance, a bad memory like myself, I usually forgot where I parked it, then I have to loop all the way in the parking lot until I found where is exactly the location of the parking spots of my car. So now we understood with this idea that is flexibility high, but again, there is other drawback, and this is what we refer to as fully associative cache. It's fully associative. There is no restriction. We're not grouping anything. There is no direct map. There is no grouping in any way associative. It's fully associative, fully flexible, can park anywhere. And they found that actually with these two clever ideas, that the miss rate could be reduced. Again, given that I didn't change the total number of students, I didn't change the total number of parking spots. Okay, if there is any other idea that I can actually use or I can employ to also reduce the miss rate, they said, yes, you can do that by having another parking spot, but it's not in the compound. It will be a little bit further, maybe 5 minutes further. Instead of parking all the way 30 minutes from your compound, there is another parking lot that we are going to build, which is 5 minutes away or 2 minutes away and stuff like that, which is a little bit larger than the parking spot on the compound, but you have to pay a little bit more. And the same idea here, that you can have second level of cache. So you might have an L2 cache, you might have even an L3 cache, and so on and so forth. It will hold a little bit of bigger space, but of course the access time would be not as quick as the L1 cache. You need to park going 5 minutes or 10 minutes walk instead of just 1 or 2 minutes walk from the compound to the parking lot. And all these ideas showed that we can actually reduce the cache miss rate. So now we have fully associative, as we mentioned. It can go anywhere in the cache entry. There is no restrictions. But I would need to require to search, of course, on all the entries. And if I would like to search by ones, so this means that I have comparator, and that would be very expensive because I have to have comparator for each of these locations. It will be very expensive. With n-way set associative, each set contains n entries. It can be 2, it can be 4, it can be whatever the number is. I'm grouping of locations together to one particular set. But the question is, if I'm grouping some of these together, how I will know exactly where is my location to park, or what is the set that is associated with my number? We said, okay, applying this formula, please block number, the number that it will be given to you, modulo the number of sets in the cache, instead of what we had earlier with the direct map when we have the number of blocks in the cache. Here's the number of sets in the cache. And again, we'll search all entries in a given set at once. Now I have n comparators instead of comparators for all of the locations, is of course less expensive. Let's take that example. Hopefully it will make things a little bit more clear. Suppose that the number that is given to you in that compound is 12. So the address that you would like to search for is 12. You would like to know Where is your parking spot in case of a direct map? In case of a two-way associative? In case of a fully associative situation? So in case of a direct map, you have number 12. I will do 2 modulo the number of blocks in the cache. The number of blocks in the cache is from 0 to 7. So I have 8 different blocks. So 12 modulo 8 is 4. So I will go there. I know that my location is 4. So 0, 1, 2, 3, 4 is my location. So I can park here if my number is 12. And it is only one location. How about two-way set associative? Again, 12, same number, 12. But modulo the number of sets. What is the number of sets if I have a two-way associative and I have a total of 8 blocks? It is just 8 divided by 2 will give me 4. In another sense, it is two-way associative, meaning I am grouping each 2 to one group. So with this, each 2 will be one group. This is one group, another group, another group, another group, total of 4 groups. Because 8 divided by 2 will be equal to 4. And I have to do modulo 4. 12 modulo 4 is equal to 0. Just I would like to highlight here that because some of you may make this mistake, that as soon as they find that it is two-way set associative, they say 12 modulo 2. It's not like that. You have to do it modulo the number of sets available in my cache. And the number of sets available should be the total number of the available slots divided by the grouping criteria, the number of grouping criteria. In this case, we are doing two-way, meaning I'm grouping 2 blocks in one set. And because of that, I have 12 modulo 4, so it gives you set 0. But when I went to set 0 here, I found actually that there is a space in the left, a space in the right. Which one I should use to park? You belong to that set, and no one give you any restrictions as soon as you have a space available in this particular set where to park. Correct? You can park either in the right or either in the left as soon as you belong to the same set. You belong right now to set 0, so then you can park anywhere in set 0. If set 0 has 2 spots and 2 spots empty, you can park either or. So there is no restriction. You can choose to park here. The slide here choose that you will park here. How about with fully associative? Again, you are 12 and you would like to know where to park. Again, as we mentioned, with fully associative, there is no restriction at all in the parking spots. Your car can park in anywhere. You can choose to park here. Another one can choose to park here. Third one can choose to park here. The slide choose that you will park here. So then you can park in any of the spots because this is fully associative. Just to understand it better, let's look at this particular distribution. Suppose right now that we have a cache with 8 entries, 0 all the way till 7. This is direct map. And by the way, direct map is one-way set associative, correct? Because grouping of 1 to 1 is just direct map. So each of the data will have its tag, data tag, and so on and so forth. I have decided to do a two-way set associative, meaning that I will group these 2 parking spot location into one set. So this will go to one set. Instead of having them as 2 blocks, it just belong to one set. One would be here, one would be here, but both of them belong to the same set. I would like to do the same between this and this. So I will have them both also in the second set, set 1. So one will be here, another one will be here. The same with this, one will be here, one will be here. The same with this, one will be here, one will be there. But just please keep in mind an important comment here. As you can see, when we moved these two to one set, they have been already moved with their own tag. So this with on tag, as an example, has been moved here. Data and the corresponding tag. Data and the corresponding tag is here. When we go to the next row, also data with its own tag has been copied there. So although they are in the same row, which belong to the same set, has the data at the corresponding tag. This is not the same situation when we had direct map with multi-word block. Because with the direct map with multi-word block, we can just add words here, but all of them will have the same tag. But still direct map. We add multi-word, but the same tag. This situation with set associative is not the same. And you will understand later on how this will affect my address scenario, or the way that we will address actually a set in a set associative. Suppose later on that I have decided even instead of grouping 2, I have to group 4 together and another 4 together. So these 4 together will be in the same row, data and tag, data and tag, data and tag, data and tag. And all of these will be belonging to set 0. And then the next 4 will be data and tag, data and tag, data and tag, data and tag, also data and tag, data and tag, data and tag, data and tag. And all of these will be into set 1. So now you can either park in this set or you can park on this set according to the number that will result from the formula. Another way you can think of this, instead of going all the way from here to here, you can go from here to here by just grouping 2 together to 1, 2 together to another one. The same concept. This is 4-way set associative. When we have 4-way set associative, how many sets do we have at the end? 8 divided by 4, I have 2 sets. This one, 8 divided by 2, I have 4 sets. And that's what I'm using to divide by in the mathematical formula. How about if I have 8-way set associative? 8 divided by 8 is equal to 1. So that means that I have 1 row. But 1 row is the same things as fully associative because I can park anywhere. No matter what is your number, you have only 1 row to park, or one basically big place to park, which you can park in any of the parking spots available in the parking lot. So we have here an example of 4 block caches, and we need to see how we will map all of these all of these situations if I have a direct map, if I have a 2-way set associative, and if I have a fully associative, given that the block access sequence is 08068. Let's see the direct map first. You will first would like to know where I should park, given that this number will be given to you, this number will be given to you, another number will be given to you, where exactly you need to park, with the direct map or with the n set associative or with the fully associative. With the direct map, we already knew that the formula is whatever the number is given to you, modulo the number of blocks, and the number of blocks given to you is 4. 0 modulo 4 is 0. So the parking spot that you need to park in is basically 0. 6 modulo 4 is 2. So the parking spot that you need to park on if your number is 6 is basically 2. 8 modulo 4 is basically 0. So where to park if your number is 8 is basically 0. Okay, and we need actually to see how it is happening exactly with the cache, but waste time. Do you remember with the example that we had 4 of these, and with time we are just tracing all whatever is happening with each one of them? Do you remember that example earlier? With each of the numbers with time? When we have all of these examples, do you remember that we had that? Now, instead of having these in 4 rows, we are just cascading these in one column. It's the same thing. I'm just rearranging them in order to have a little bit of a space. That's all. This location, if you recall, was 0, 1, 2, 3. Here is we have the 0, location 0, location 1, location 2, location 3. Location 0, 1, 2, 3. And this is the block address. I begin with 0. And then all of whatever I have here is with time, with different time instance, different snapshot with each of the row. So with this very first row, I would like to access memory of 0. I will go to location memory of 0, which is here. Of course, at the beginning, I had nothing. So when I would like to search for memory of 0, I didn't find anything. So I miss. Correct? I didn't find whatever I'm looking for. So when I miss, what I should do? If you were studying at your desk and you just suddenly found that you are missing something important with the materials that for the exam for tomorrow, what you will do? Just go directly to bring whatever you had missed in whatever the place that you know exactly that is there, either in the library or in the storage unit or where it is, and then bring it to your location, correct? This is what we will exactly do here. As soon as I know that I miss, I will go all the way to the main memory and bring it back to me to the cache. So basically, I will bring the memory of 0 and copy it here. The next instance of time, I would like to access memory of 8. I would like to access block address of 8. Block address of 8 means I need to park in 0. So again, I will go to C location 0. Do I have there memory of 8? Unfortunately, what I had earlier is memory of 0, not memory of 8. So I miss. So I didn't find whatever I'm looking for. So I miss. What I will do if I miss, I'll go to the main memory, bring a memory of 8 with me, and copy it to the cache. This is the CPU. This is the cache. Let's say L1, and this is my main memory. I go to this location to find the data that I'm looking for. I didn't find it, so I miss. What I will do, I will go to the corresponding location here in the memory and just copy the data that I had to the cache, and then the CPU can use it easily. Okay, so I miss, copy to memory of 8 to memory of 8 is here. Then the next thing, I would like to access memory of 0 again. 0 is parking 0, so I will go to 0. Oh, 0, I just found that I had memory of 8. So again, I miss. What I should do? Override memory of 8. So as you can see from here, 0, 8, 0. So always miss, because I just, each time I'm overriding whatever I had from the previous step. And this is what called would be the worst case scenario, correct? This is ping pong situation. Ping pong situation meaning that each time I'm just overriding whatever I had from the previous step. And I will always miss in this particular scenario. Then I need to go to 6. Oh, 6, meaning that I need to park to 2. So, oh, that's 2. I will go here to 2. Is memory of 6 there? No. Of course, previously there was nothing there. So again, I miss. What I should do when I miss, copy memory of 6 to this particular location. The last thing is memory of 8. Memory of 8, this means that I need location 0. I will go to location 0. Unfortunately, previously I had memory of 0. So again, I miss. I need to overwrite it and write memory of 8. So as you can see from here, all of these, that all of my attempt I misses in the whole scenario. Let's try to see if I have a two-way set associative, what would be the case? Again, remember, that I need to take the block number that is given to you, the number that is given to you, modulo the number of sets. How much is the number of sets here? If you recall, I have 4 blocks. So 4 blocks. So I have 4 blocks. And I have 2 ways of set associative. 2 ways of set associative means that I am grouping each two to one group, another 2 to one group, or to one set. So how many sets total? 2 sets, because 4 divided by 2 is equal to 2. And that's why I have these 2 here as 4 divided by 2 as opposed to 2 way. Some of you may make this mistake that will just say, oh, 0 modulo 2, 2 because 2 way set associative. It's not like that. 2 because 4 divided by 2 is 2. I have 4 different locations. I'm grouping each 2 in one set. So this will be one set. This will be another set. So I have 2 sets total. So 0 modulo 2. 0 modulo 2 is 0. 6 modulo 2 is 0. 8 modulo 2 is 0. Oh, so all of them need to park in the same set. But I already knew since it is 2-way set, so I know that each set has 2 parking spots. We'll begin again as usual, but now instead of having 4 different locations or different groups, now I have one set that is grouping 2 locations, another set that is grouping another 2 locations. With 0, I will go to set 0. I will look either here or there. Did I find the memory of 0 initially? No. So I miss. What I would do when I miss, go to copy memory of 0 into the set 0. When I copied memory of 0 to that set 0, I found that this spot is available and also this spot is available. Which one I should use? It's up to you. Can be either or, because there is no restriction. You can park right, you can park left. There is no restriction at all. Restrictions at all. Then I will go to memory of block address 8. Where is 8 to park? Again, set of 0. When I look here and here, I hadn't memory of 8, so I miss. Then memory of 8, I will bring it from the main memory. As an example, I found that this spot is already taken to memory of 0. This is empty, so please copy memory of 8 here. So memory of 8 is copied here. Then block 0 again to set 0. So I will go to set 0. I found set 0. Oh, I found that memory of 0 was basically here, so I hit. So I don't have to do anything. Then 6, where is 6? 6 in 0 again. So I will look at here and here. I didn't find memory of 6. I found earlier memory of 0 and memory of 8. So I miss. I will go to bring memory of 6. And I need to allocate memory of 6 in either the right location or the left location. Or in another sense, I need to override either memory of 0 or memory of 8. Which one I should override? Should I override memory of 0 or should I override memory of 8? There are actually different ideas in this scenario. One idea said that you can randomly kick one of them. Kick out one of them. You can either kick out memory of 0 or you can kick out memory of 8. Another idea said, no, we would like to be a little bit fair. So let's kick out the one that stayed longer and keep the one that is just came. With this example, memory of 0, I was just asking for, so it's just there. Memory of 8 was older a little bit. So let's overwrite memory of 8 and write memory of 6 on that particular location. This is called least recently used. This idea of replacement called least recently used. And of course I miss. Then the last one with the 8, With the 8, where to go? 0, I will go here. I will go here. It's memory of 0, memory of 6. Memory of 8 is not there, so I again miss. But again, with the same scenario, when I bring memory of 8, should I override memory of 0 or should I override memory of 6? Memory of 6 just arrived, correct? So it hasn't been there a lot, so just keep it, then override memory of 0, and that's why memory of 8 override memory of 0 in this situation. And as you can see in this scenario, that I have only one hit among all of the situations, or among all of the attempts that I had, I just have one hit. How about this fully associative example? When I have all of the locations available to me, there is no restrictions. So memory of 0 can park either here or here or here or here. But when I went, I didn't find memory of 0 in any of these locations, so I missed. I will go to bring memory of 0 from the main memory, and I can allocate memory of 0 or copy memory of 0 in any of these situations. The slide it shows here. Another one can choose here. Another one can choose here. Another one can choose here. It depends on your decision. Then 8. I will go to search in all of the locations. Did I find memory of 8? Of course not, because initially memory of 8 was not there, so I missed. And then I will copy memory of 8. This location is already filled with memory of 0. Then I choose this location to copy memory of 8. But you may decide here, another one may decide here. Then the 0. The 0 is there already, so I hit. Then the 6. I didn't find memory of 6 in any of this location. So I found that this is spot and this is spot available. So I have decided to copy memory of 6 in this particular location. But of course I missed. Then memory of 8. Memory of 8, oh, it was there, so it is there. I hit. I don't need to do anything. As you can see from here, I have 1, 2 hits among all of my attempts, increasing a little bit my hit rate or decreasing my miss rate. And this again with probability. There is no guarantee that this will be the situation, but it's just with probability. So increasing the associativity will decrease the miss rate, but with less or diminishing return. As you can see from here, let's say that we are simulating a system that is 64K with 16 word block. With one way or direct map is 10.3%, the miss rate. With two way, as you can see, like significantly less to 8.6. But from two way to four way, from 8.6 to 8.3, each time is just diminishing the benefits of using a higher set of associative. 8-way associative, I'm going from 8.3 to 8.1 and so on. So there is limits, but afterwards, I will not get really a serious or a really big benefit of increasing the number of set associative. Let's see that example. So now, with this cache, I have from 0 all the way till 255 different floors. So I have total of 256 different floors. And I have many buildings here, 1, 2, 3, 4 buildings. And inside one building, with this floor, inside that building, I need to know how many rooms can I address. They said that this is 32 bits. 32 bits meaning that I can address actually 4 bytes or 4 different rooms, correct? The first question that I need to ask myself, how many bits do I need to address any of the rooms? So room 1, room 2, room 3, room 4. How many bits do I need? 2 bits, correct? Because log 2 to 4 is equal to 2. 0, 0, 0, 1, 1, 0, 1, 1. So I need just 2 bits to address any of these locations, correct? How many bits do I need to address any of the floors? Again, log the base 2 to 56 is equal to 8. And that's why here I have 8 bits to address my floors. But how to address which buildings? Either this building or that building or that building or that building. Here is a new situation that we haven't discussed earlier with the direct map. Interestingly, here I have a total of 32. 32 minus 8 minus 2 will give me 20, so 22, sorry. So I have 22 bits of tag. I will take these 22 bits of tag. I will compare it to the tag here. I will compare to the tag here. I will compare to the tag here. I will compare to the tag here. And the one that matches will be the correct build. So now I have been able to specify the room number. I have been able to specify the floor number. I have been able to specify the building number by not the same situation as I had with the direct map. What is the difference? The difference right now that with each of the buildings, I have a tag associated with the building. Wasn't the case with the direct map, if you recall. With the direct map, we have it like that. This is one like this, and we have different words like that. But each of all of these will have the same tag. Okay, how about if it is set associative, but we have also multi-word situation? Meaning the block, each block will have multi-word. How we can address these? Same concept. We will address the room. This will be here. And then we will address which word. Then we will add something in between here. And then we'll address the floor with this. And then we'll address the tag which of the building. And so on. So with the replacement policy, as we mentioned earlier, with the direct map, there is no choice, of course. You just have one particular only choice. So there is no choices. But with the set associative, one rule that we mentioned is least recently used, meaning that you will kick off the one that stays more, and you will leave the one that it just came on. So choose the one unused for the longest time. Of course, implementation-wise, this will be simple for 2 ways, manageable for 4 ways, but then begin to be too hard when I have even multiple of these, just implementation-wise. The other option that you just choose randomly, you can just kick out any of them. It's just randomly, and there is no rule that will manage all of these things. So with these multi-level caches, of course, primary cache will be attached to the CPU, small but fast. The level 2 cache, it will miss whatever you miss from the L1 cache. You will go to the L2 cache, and that's why it will be larger, but it's not as fast as the L1 cache, so it's a little bit slower, but of course faster than the main memory. Then the L2 cache misses will be basically handled from the main memory. So if I miss anything in the L2 cache, I have to go to the main memory. Some even high-end systems include L3 cache. Let's take this interesting example. Assuming right now that I have a CPU and I have an L1 cache, and assuming that I have a main memory. Tells you here that the base CPI is 1, clock rate is 4 gigahertz, the miss rate per instructions is 2%. The main memory access time is 100 nanoseconds. So when I try to find something here and then I miss 2% of my time, I'm going to the main memory. And each time I go, I have to pay 100 nanoseconds. Okay? But first, I need to know, since we deal with the clock cycles, I need to know how many clock cycles I have if I need to pay, or how much counts 100 nanoseconds in terms of cycle. So you can just say how I calculate the miss penalty in terms of cycles. How to calculate that? I know that it is 100 nanoseconds to pay. And I know my clock. Correct? I know my clock rate is 4 gigahertz. So my frequency is 4 gigahertz. How much is this T? T is 1 over F. Correct? So if I divide all of these to this, divided by this, it will give me how many clock cycles? Correct? The total 100 divided by the time of one cycle. So 100 divided by the time of one cycle, which is 0.25 nanoseconds. In this case, if this is 4, because 1 over 4 gig, it will give you 400 cycles. So each time I need to pay 400 cycles if I would like to go to the main memory. So what is my effective CPI? It will be the base CPI, which is 1, plus 2% of the time I have to pay 400. So 2% of the time multiplied by 400 plus 1, it will give you 9. Correct? So now, each time I have to pay 400 cycles if I miss something in my L cache. And accordingly, my effective CPI right now will be 9 instead of 1. Can you see the difference? So let's take this example. I have a CPU. I have an L1 cache. I have an L2 cache. I have a main memory. Given that I still have 400 clock cycles if I would like to go to the main memory. So here it says access time is 5 nanoseconds, as opposed to 100 nanoseconds in the main memory. This with the L2 cache, the access time is 5 nanoseconds. Okay, so 5 nanoseconds instead of 100. This is 5 nanoseconds. And I have, again, 4 gigahertz. So this is T, 5 divided by T. In this case, will give you 20 cycles. So this means that each time I miss something here and I need to go to L2, I am paying 20 cycles. How much percentage of the time? Its miss rate per instruction is 2%. So 2%, I have to pay 20 cycles. But the global miss rate to the main memory is 0.5%. What is the global miss rate to the main memory? Meaning that I went here, I didn't find what I'm looking for. Then I went here, I didn't find what I'm looking for. Then I went here. This situation happened to go to the main memory 0.5% out of my time. How much I have to pay with each time I'm going to the main memory? 400 cycles. How much will be my total effective CPI? The ideal is 1. So 1 plus this multiplied by this plus this multiplied by this. So 1 plus 2% multiplied by 20 plus 0.5% multiplied by 400 gives me 3.4. Remember that when we have added an L2 cache, it gives me 3.4. When we had it L1 only, it gives me 9. So basically 9 divided by 3.4, so 2.6 is the ratio difference between them. So with this multi-level cache consideration, I have a primary cache that's focused in minimal hit time. The L2 cache will focus, of course, into lowering the miss rate to avoid the main memory access. The hit time has less overall impact in this case. And of course, the result that L1 block size will be smaller than the L2 block size. And this is just a summary of all whatever we have covered in the cache: temporal locality, spatial locality, different categories of cache misses, compulsory misses, conflict misses, capacity misses. Of course, the worst case scenario when we have a ping pong effect, as we have introduced. We mentioned also the associativity, the replacement policy, the right high, the right hit when we have right through or right back, right miss polity when we have a right allocate or right buffer.